Now, having told you that I've made things more complicated, we need to appreciate that there are ways in which I can relieve all your fears, all of your burdens, by remembering back to a lecture I gave on complex equilibria and to the very last little conversation piece I had with you there when I talked about how it was that we make assumptions involving acid-base chemistry about when stuff matters and when stuff doesn't. And if you remember, I told you that when we talked about concentrations, if our concentrations differed by a couple orders of magnitude from each other, then I could ignore the lower concentration. That's why we ignore 10 to the minus 7 for water if anything's above 10 to the minus 5 molar around it for the protons. But just as importantly, I told you that when you look at the K values, if your K values are 3 or 4 orders of magnitude apart from each other, then under those circumstances, you can ignore all the other K values around it. So if I look at this problem right here involving carbonic acid, even though there are 2 K values to deal with, there is the removal of the first proton, there is the removal of the second proton. The fact that these K values are so far apart, 6 orders of magnitude or more apart, not just 3 or 4, but 6 orders of magnitude apart, means that I don't have a diprotic acid problem. I have 2 monoprotic acid problems. There's one of them, and that's what happens when you're working in an acidic environment. This particular K value is so far away, I don't even care about it. Only this one matters. In the same way, when I'm working in base, this is going to be the only species that matters, and this one gets to be ignored. So our rule of thumb rears its head and says, if our K values are 3 or more orders of magnitude apart, I can treat polyprotic acid cases as a collection of monoprotic cases. Why is that such a good thing? You know how to do monoprotic acid problems. If they're weak, H plus is equal to KaCa to the 1/2. If it's a buffer, H plus is equal to KaCa over Cb. See, I can use the monoprotic acid cases if my Ks are far apart. Just think about it. If in a polyprotic acid my Ks are far apart, I can treat everything using the simple approximations for weak acids, weak bases, and their buffers. So I look at this case here with phosphoric acid, and it's as if there's a God out there who said, you know, let's take the 2 most famous diprotic and triprotic acids there are. The carbonic acid system that delivers limestone quarries, that delivers bicarbonate of soda, that delivers carbon dioxide dissolving itself in water as carbonic acid. And let's take the phosphoric acid system, the one that makes our sodas acidic, the one that serves as the buffer in the blood system of our bodies. And in each of those cases, check out those Ks. They're 5 orders of magnitude apart from each other. They're 6 orders of magnitude apart from each other. I don't have a diprotic acid. I don't have a triprotic acid. I have 2 monoprotic acids. I have 3 monoprotic acids. And now my calculations are easy ones to do. Of course, that bit of luxury goes away pretty quickly when I look at the real world. In the real world, this is rare. Of course, these are the problems I make you work over and over again because all they require you to do is recognize that you can ignore other K values. If it's a pH around 7, ignore these guys and just work the problem. If it's a pH that's really low, ignore those others. That's not real life, though. In real life, welcome to something like tyrosine right here, a nice amino acid. Notice it's got 1 K that's very acidic. That's great. If I can work in this region here in acid, this is the only proton I worry about. But look at these other K values. These other K values are within an order of magnitude or so of each other, so I cannot talk about this K value and ignore this one. I cannot talk about this one and ignore this one. In other words, because my Ks are close together, I cannot approximate that a single K will explain it. It's no different than when we were looking at KWs and said, you can't have methanol with a 10 to the minus 14 K value be around KW of water 10 to the minus 14 and ignore the KW. If you've got 2 K values that are near each other, you have to work one of these sorts of complex equilibrium calculations so that the Ka and the Kw are there at the same time. Well, this is no different. I've got to come up with some sort of complex equilibrium solution in which these Ks are accounted for at the same time. At that point, I have to think about the lecture on complex equilibria that we just finished and say, all right, tyrosine, what's in solution? H plus and OH minus, H3T, H2T minus, HT minus 2, T minus 3. Oh, wow. I've got all of that to take care of. That's 6 unknowns. I need 6 equations, so I write down the Kw equilibrium. I write down the Ka1, Ka2, and Ka3 equilibrium. I throw in a mass balance. I throw in a charge balance. I've got 6 equations, 6 unknowns. You know the drill. Matrix inverse, crank out the right answer. That's how I have to do this problem here. Except it's general chemistry. We're not going to bother with it. All we're really going to do is appreciate the fact that this is what you would have to do in a polyprotic acid if I didn't give you something like carbonic acid and phosphoric acid. In the real world, complex equilibria, you've got to go through that whole process to end up with equations that are not approximations, because the approximations that work up here and here do not work down here.